Chapter 5.1 Working with Radicals. Reminder, we have the radicand under the root sign, and then the number that indicates the root is called the index. Restrictions on variables. When a radicand contains variables, identify the values of the variables that make the radical a real number by considering the index and the radicand. If the index is an even number, the radicand must be non-negative. For example, in the square root of 3n, the index is even, then the radicand must be non-negative. So our restriction would be that 3n has to be greater than or equal to 0, which therefore means that n has to be greater than or equal to 0. Note, a variable to the power of an even number will always be non-negative. So x to the power of 2, x to the power of 4, x to the power of 6, x to the power of any even number is always going to result in something greater than or equal to 0. Why is this? Because a negative number, let's say negative 3 to the power of 2 or any other even number, is going to be negative 3 times negative 3, or negative 3 times negative 3 times negative 3 times negative 3, however many times we have the exponent. And because it's an even number of times, a negative times a negative equals a positive. So if it's negative 3 to the power of 2, we get positive 9. Simplifying radicals, changing entire radicals to mixed radicals. Write the radicand, the number underneath the radical sign, as a product of a perfect square or cube or whatever index you're doing, and another number. So the square root of our unsimplified radical equals the square root of a perfect square times the square root of another number, or the cube root of our unsimplified radical equals the cube root of a perfect cube times the cube root of another number. Then you can square root or cube root the perfect square or cube portion. Let's make a list of our perfect squares and perfect cubes so that we have them to use. 2 squared is 4, 3 squared is 9, 4 squared 16, 5 squared 25, 6 squared 36, 7 squared 49, 8 squared 64, 9 squared 81, 10 squared 100, 11 squared 121, 12 squared 144. We also have variables. Perfect squares of variables would be x to the power of 2, x to the power of 4, x to the power of 6, x to the power of 8, etc., x to the power of any even number. Perfect cubes. 2 to the power of 3 is 8, 3 to the power of 3 is 27, 4 to the power of 3 is 64, 5 to the power of 3 is 125, 6 to the power of 3 is 216, 7 to the power of 3 is 343, and 8 to the power of 3 is 512. And then for our variables, x to the power of 3, x to the power of 6, x to the power of 9, x to the power of 12, x to the power of any multiple of 3. The fourth root of m to the power of 7. First, we need to state the restrictions. We want to do that before simplifying. In this case, our index is even. If we have an even index, then our radicand must be greater than or equal to 0. M to the 7 has to be greater than or equal to 0. The only way for m to the 7 to be greater than or equal to 0 is if m is greater than or equal to 0. So m has to be greater than or equal to 0 is our restriction. Now we can simplify. We want to write m to the 7 as m to the power of 4 times m to the power of 3. We know from our exponent laws, m to the 7 is the same as m to the 4 times m to the 3. Then we can take the fourth root of m to the 4, and we get m times the fourth root of m to the power of 3. Next example, we have an odd index. Therefore, there's no restrictions. When you have an odd index, you can have negative values under the root, so there are no restrictions on the radicand. Let's simplify our radicand. We have the cube root 16. We want to split up into a perfect cube and another number. We can divide 16 by 8, which is a perfect cube. We have 8 times 2. Then we have a to the 6. Because 6 is divisible by 3, we can leave it as a to the 6. We want our exponents on our variables to be divisible by the index. B to the 5, we need to split up into b to the 3 times b to the 2. Then the items that are perfect cubes, which are 8, a to the 6, b to the 3, we can cube root them and take them out. We get 2. When we cube root a to the 6, we get a to the 2. 6 divided by 3 is 2. And then the cube root of b to the power of 3 is b to the 1, or just b, times the cube root of 2b squared. The square root of 63 n to the 7 p to the 4. The index is even, so we have restrictions. We need 63 n to the 7 p to the 4 to be greater than or equal to 0. We can divide both sides by 63. Then we get n to the 7 p to the 4 has to be greater than or equal to 0. And then let's take a look at our variables. We have n to the 7, so that's an odd exponent. And then we have p to the 4. But we said up here that a variable to the power of an even number will always be non-negative, because we had this example, negative 3 squared is negative times a negative, which gives us a positive. So n to the 4 is always going to be greater than or equal to 0. So really the only thing that's going to determine whether our radicand is greater than or equal to 0 is that n to the 7 has to be greater than or equal to 0, which means n has to be greater than or equal to 0. That's our restriction. Now let's simplify. We want to write 63 as the product of a perfect square and another number. The biggest perfect square that can divide 63 is 9. We get 9 times 7 times. Then we want to split our n to the 7 into n to the power of something that can be divided by 2. So n to the 6 times n. And then p to the 4 is already a perfect square, so we can leave it as that. Then we want to take the perfect squares out from under the root, which are 9, n to the 6, and p to the 4. And we get 3 n to the 6 divided by 2 is n to the 3. And p to the 4 divided by 2 is p to the 2. And then we have the square root of 7n. Mixed radicals to entire radicals. So going back the other direction, same process. We're still going to state our restrictions before we do anything. and then we're going to move everything back under the root sign. Restrictions on square root of t. T has to be greater than or equal to 0. To move this t to the 3 underneath, we have square root, so we need to square that to move it underneath. So t to the 3 to the power of 2. We get the square root of t times t to the power of 6. Power of a power rule, 3 times 2 is 6. And then we simplify that to t to the power of 7. Product rule, we add the exponents. Next one, index is odd, therefore we have no restrictions. We want to bring 2m squared underneath the cube root. We're going to have to do 2m squared all to the power of 3. We get the cube root of 4m times 2 to the power of 3, m to the power of 6. So power of a product rule, we apply this 3 into the brackets to each term of the product. So we get 2 to the 3, and then m to the 2 to the 3 is power of a power rule. Multiply the exponents, we get m to the 6. Then we want to simplify. Cube root of 2 to the power of 3 is 8. 4 times 8 is 32. M times m to the 6 is m to the 7. Cube root of 32, m to the 7. 3a squared b times the fourth root of 2mn squared. This is an even index, so we have to set the radicand greater than or equal to 0 for our restrictions. Well, we can divide by 2, then we have mn squared is greater than or equal to 0. But we know that a variable to the power of an even number is always a non-negative number. So n squared is going to be greater than or equal to 0 no matter what, which means really it's just m is greater than or equal to 0. That's our only restriction. If we want to move the 3a squared b underneath, we're going to have to raise it to the power of 4. So 3a squared b to the power of 4. This 4 is going to apply to each of these terms of the product. Then we get the fourth root of 2m n to the 2 times 3 to the 4, a to the 2 to the 4. That's the power of a power rule. So a to the 8, and then b to the 4. Let's simplify. Fourth root of 2m n to the 2. 3 to the power of 4 is 81. A to the power of 8, b to the power of 4. And then multiply our numeric coefficients together. We get the fourth root of 81 times 2 is 162. And then I'm just going to put my variables alphabetically. You don't have to. A to the 8, b to the 4, m n to the 2. Our numeric coefficient should go at the beginning, but the order of the variables doesn't really matter. Adding and subtracting radicals. You can only add or subtract like radicals. Like radicals have the same index and the same radicand. For example, 2 square root 5, 10 square root 5, and negative 4 square root 5 are all like radicals because they all have square root 5. Another example, the cube root of 2 9 times the cube root of 2, 7 times the cube root of 2, and -5 times the cube root of 2. Those are all like radicals because they all have cube root 2. State restrictions on the variables, fully simplify radicals, and combine like terms. First one doesn't have any variables, so we don't need to worry about restrictions. What's the biggest perfect square that divides 24? We have 4, 9, 16. It is 4 times 6 is 24, and then plus the square root of 6. We can take the square root of the 4. We get 2 times the square root of 6 plus the square root of 6. These are now like radicals. They both have square root 6. We can add them together just like we were adding 2x plus x. So we have 3 square root 6. Square root 20x minus 3 times the square root of 45x. Our restrictions: we have x under each root and their square roots. So we'd say that x has to be greater than or equal to 0. What's the biggest perfect square that divides 20? It would be 4. 4 times 5x minus 3. The biggest perfect square that divides 45 is 9. 9 times 5x. We can take 4 out from under the square root and take 9 out from under the square root. We get 2 square root 5x minus 3 times 3 square root 5x, which simplifies to 2 square root 5x minus 9 square root 5x. And then we have like radicals. They both have square root 5x. We can combine them. We get -7 square root 5x. Last one, the cube root of 8a to the 4b minus the cube root of 27a to the 4b. Restrictions: well, we have an odd index, therefore we have no restrictions, because we can have negative numbers under cube roots or fifth roots or any odd root. We want to simplify. What's the biggest perfect cube that divides 8? It's 8. 8 happens to be a perfect cube. Cube root of 8. We want to split a to the 4 up so that we have a exponent that's divisible by 3. So a to the 3 times a. Then we have b minus the cube root of the biggest perfect cube that divides 27 is 27. Again, it's a perfect cube. A to the 4 we want to split up as a to the 3a, and then we have b. We can take the cube root of 8 and the cube root of a to the power of 3. We can take the cube root of 27 and the cube root of a to the power of 3. We get cube root of 8 is 2. Cube root of a to the power of 3 is a. And then we have cube root of ab minus the cube root of 27 is 3, and the cube root of a to the 3 is a. And then we have the cube root of ab. These are now like radicals because they both have the cube root of ab, and we can combine them. 2a cube root ab, and then minus 3a cube root ab. We have 2 of something, we take away 3 of something, we then have -1 or -a cube root ab. That brings us to the end of lesson 2 for chapter 5.